Welcome to the second video of the video series about test.con 6 Studio. In this part I'm going to program a simple real-time application and I will show you how you can access I/O variables of the Q.blocks modules. In the picture you can see the structure of the Q.station. Physically, the Q.station is one device. Logically, however, it consists of various devices. On the right side, you can see the high-level section with 3 test.con kernels, which are graphically programmable. The red circled area is the real-time kernel of the Q.station. This is the low-level section where a program is processed in hard real-time. This time, the cycle time in which the program is processed in the real-time kernel is not set in test.con, but test commander. On the screen you can see the dialog for setting the cycle time. At the moment we have a cycle time of 10 kHz. On the screen you can see the IDE of the programming system test.con when no project is loaded yet. I will now create a project for the real-time kernel. For that matter, there is a dialog in order to choose a template for the application. I choose the real-time application and name it My RT Project. You could also insert a path to the directory you want to save your project at, but it is not necessary for this example. Now you can see the system context diagram for a real-time application. In the upper section, you can see the structure of the Q.station. Up here, you can find the high-level section with a graphically programmable user space app. Right here, the start app with the communication block to the user app is shown. Below, drawn a little bit stronger, there's the real-time kernel of the Q.station with the data acquisition system for the communication with the Q.blocks modules. Then left there's a program block of the real-time application with a connection to an interface, the so-called app connectors. The real-time application has immediate access to the data acquisition system and it can access all variables. Furthermore, the real-time application is called simultaneously to the data acquisition system. Every program block has a worksheet, on which the block diagram of the application can be written. You can call the worksheet by clicking the command Edit in the context menu. Now you can see the block diagram of this application with a macro block. The macro block maintains the communication to the start app. The name and other information are transferred to the start app. I will talk about the block a little later on. For now, we will leave it on a worksheet and we will use the free space for our application. On the webcam screen down right, you can see a Q.station with Q.blocks modules. Furthermore, you can see tweezers with an attached strain gauge. The strain gauge changes its resistance when the tweezers are pressed. The resistance change is transformed over the bridge circuit into a voltage change. This voltage change is measured in the A101 module and can be accessed in the application accordingly. The example which we will now program is a particularly small example, where only the minimum and maximum value of the tweezer's deformation is captured. For that matter, only one function block is needed. I will now search for it in the favorites tree. Here I can find a section with the function blocks signal analysis, signal processing, and also the function block min-max. Now I can drag this function block into the worksheet. There is another way to find this function block too. At the bottom left, we can search the function block through the command find block. If I look for min, the search engine will find the min-max function block. Want more information about the function blocks? You can find an online help by right-clicking on the function block, which will open the context menu, and select Help. Furthermore, you can find tutorials, examples, and manuals on the test.con website under www.test.con.info. Now back to programming. I will assign the measurement signal of the tweezers to the function block. Therefore, I will zoom into the worksheet. There are two possibilities to assign the signals. On the one hand, you can use special function blocks from the library device data access function. On the other hand, you can dock attributes to the inputs and outputs. An attribute is, for example, a variable. There are two possibilities to assign the signals. On the one hand, you can use special function blocks from the library device data access function. On the other hand, you can dock attributes to the inputs and outputs. An attribute is, for example, a variable. I will show you the second method mentioned. When I call the command now, a data point management window will open. Here I can, for example, assign variables for the communication in the application. Here you can see the section GIO or Gantner-IO. The field is still empty, which means the program does not have a connection to the Q.station yet, and it could not yet read the configuration either. Now here you can see the section of the app connectors. I will talk about this section a little more in part 2. To read the configuration now, I will call the command import Gantner-IOs. The programming system now scans the office network for suitable controllers and finds a controller, which is the Q.station, which is right here on my table. You can see two logic devices here. One is the real-time kernel and one is the Linux-based user space kernel. Theoretically, the startup should be seen here, but it is suppressed in this dialog, so you cannot accidentally reprogram the startup. Now you can see the section which was called Gantner-IO before. Now it has been replaced by Q.station IP DT. When selecting the section above, you can see all variables which are available for this application. You can also select the single modules. In this case, the A104 and the two A101 modules which are connected to the Q.station. And the last A101, you can find the tweezers now. I am choosing the tweezers now and dock them to the function block. To test the function of our small program, I will implement special function blocks which are used for the visualization of the program variables. To do so, I will go to the library visualization and select the box display numeric and place it on the worksheet and connect it with the maximum value output of the block. Now I will implement another function block and connect it with the minimum value output. You can see that the function blocks have automatically adapted to the data type of the input signal. I will now directly load the program into the real-time kernel of the Q.station. To do so, I will use the command download. The programming system has now changed the system state. It is now in run mode. This is the mode in which I can view the application online. However, I cannot change the structure in this mode. As you can see, there is no favorites tree with function blocks. In this mode, no function blocks can be implemented. the same time, the system requests to choose the target system into which I would like to download the program. Up here, you can see the real-time kernel of the Q.station, and below there is the PC simulation of test.con runtime. That means I can test the application offline with the PC before downloading it on the controller. It makes sense with bigger applications, or if I simply do not have a Q.station at hand. I'll now select the real-time kernel of the Q.station. Here a program is already loaded. This program is overwritten right now. With the online visualization, I can now see the actual values. The programming system now reads the data packages from the Q.station to indicate them accordingly. However, you do not have to place such a function block if you only want to read the signal value. You can also just click on the regarding signal line to see the signal values. Okay, so that was it for this part of the video series. I hope I can welcome you in the second part of my video series again. The next part, I will show you how to pass on the results of the min-max analysis to another application. I will also show you how to implement the reset input in another application, which has an HMI. Thank you for your attention, and I hope I will welcome you in my next video.